email it to you then if we make corrections?
I'll make the correction so you can have more than one submission.
Okay.
And then everybody can. And if for any reason you cannot submit it or it makes you an error, then yeah, send me by email. Just let me know. And okay, so we'll start with the new topic today, but I want to go through some of the homework just in case if anyone has a question or anything. So I know that many people have problem with the last, have issues with the last problem, the one with the box on the wall. Yeah. So I'll do that one, and then we'll do other things. So I'm recording. So let me switch to. Oh crap! That's what I come 10 minutes earlier to prepare all this. I completely forgot. Oh, great. My computer just went dead. Oh, shoot. Oh, look at that. Okay, so same as always, if you guys in the chat have any questions, just open your mic and you can ask it. So I'm gonna go on this problem on the homework. You have a wall made out of wood, and then you have another box also made out of wood. The mass of this box is 1 kilogram, and you apply a force of 12 newtons at an angle of 30 degrees.
Yep.
Yeah. Okay. And what we want to find out is if this box moving, if the box is moving, in what direction, or something along those lines. And we know that we have wood on the wall and we have wood on the box, and we also know that the box is static. And I think those are the piece of information that we need right now. Now, the reason that they give you the material, wood and wood, is because you can then find out what is the static coefficient of friction. There's a table in your textbook with all these values. I don't remember the page, but I think for wood and wood, you have a static coefficient of 0.5. Okay, so I'm gonna look at the free body diagram. I'm gonna look at the forces that I have, and I'm gonna have a normal force away from the wall. I'm gonna have the weight pulling down. I have this applied force that I'm gonna move over here. That's gonna be my applied force. And then I have friction. Now for friction, I have two choices. Friction can either go up or it can go down. And in general, when you have an unknown variable, when you have an unknown friction, and you have a choice, or basically pick whatever you want that friction to go, pick the one that makes your force positive, just so for convenience in the math, and so you don't have to deal with the signs. So I'm going to assume that my friction is going to go this way, unless it's very obvious that it's going to go in the opposite direction. But if you can choose, pick the positive one. So I'm going to do my free body diagram. X and Y. And the free body diagram It's gonna look like that. Now, what I'm gonna do is I'm gonna calculate the friction force that I have when I apply this force. And what I'm gonna do is I'm gonna compare that friction, that static friction that I calculated, I'm gonna compare it against the maximum friction that I can have. And I know that if the magnitude of the friction is bigger than the maximum value, if I'm above that threshold, it means that the box is moving. If it's less than that threshold, the box is gonna be static. So I'm gonna just calculate for this. So I'm gonna assume that the box is static. So the forces in X are gonna be equal to 0, and the forces in Y are also gonna be equal to 0. So in the X direction, I'm only gonna have two forces. I'm gonna have the X component of the applied force plus the normal force gonna be equal to 0, and this is gonna be minus 12 cosine of 30 plus the normal force. That's gonna be equal to 0. So the normal force is gonna be 12 cosine of 30, and this is gonna be 10.4 newtons. Okay. Now in the Y direction, I'm gonna have, I think, three forces. So I'm gonna have the Y component for the applied force. I'm gonna have the force of friction, and I'm gonna have the weight. And that's gonna be equal to 0. So the applied force, that's gonna be 12 sine of 30 plus the friction force minus 9.8. That's gonna be the weight. And that's gonna be equal to 0. I'm gonna solve for the friction force. And the friction force is going to be 9.8 minus 12 sine of 30. Sine of 30 is 0.5, so this is going to be 6. So at the end, you end up with a friction force of 3.8 newtons. Okay? Now, this by itself doesn't tell you if it's moving or not. You need to compare it with the maximum force, with the maximum friction force. So the maximum static force, that's going to be mu s times the normal force. So this will be 0.5 times 10.4. So this will give you 5.2 newtons. Okay, and in this case, because the static friction that I calculated is less than the maximum value that I can have, it means that the box is static. If I have ended up with a friction of 5.3 or 6 or whatever, because it's above the threshold, then the box will be moving. Okay, and depending on the direction of the friction, you can figure out if it's moving upwards or downwards. Okay, makes sense. And Kaylee, you wanted 6.32, 63?
Yeah, I'm figuring out where the angle goes in the free body diagram.
Okay, so I'm just gonna do the free body diagram. So 63, that's the key that's on a slide. And I'm gonna, instead of drawing the key, I'm gonna draw a box. Because, just because. So the kit has a mass of 23 kilograms. There's a force here of 30 newtons. This angle over here is 38 degrees. Let me see. we have the weight. And we're gonna have friction. Okay, so those are gonna be all the forces that we have. So we only have three forces. We have the weight, the normal force, and the kinetic friction. Oh, normal force. Oops. Normal force. There you go. So I'm gonna do the free body diagram. I'm gonna place a reference frame, and I'm gonna put the x-axis parallel to the ramp. So the x-axis is gonna be like this, and this is gonna go like this. Okay. So this is gonna be my y-axis. It's gonna be my x-axis, and from here. So I'm gonna have the friction going backwards. I'm gonna have the weight here. This is gonna be 38 degrees. Now between the weight and the pool, there's a 90-degree angle. So I'm gonna have here the pool. This is a 30 Newton angle. I have the normal force along the y-axis, and this one has to be 38, I think. Let me, I don't have, oh crap, I forgot my calculator. And I don't have my, oh no.
I guess I'm just still confused on how you deciphered that the angle was 38 degrees at both of those points. Like, can you explain
So
that goes?
this angle is always going to be equal to the sum of the tilted angle. Now this, the one on top, so this and this vector, they have 90-degree angles. They're perpendicular to each other, just because of the drawing. So this is going to be, this is 38. I'm drawing this part of the force. This is going to be the weight. If this is 38, this is going to be, oops. This is going to be 52 degrees. Oh, I'm sorry. Then this is going to be 38. Sorry about that. And that's going to be 38. Yeah, so between this vector and this vector, you need to have 90 degrees. So if this is 38, this is going to be 52, and then you subtract 90 minus 52, and then you're going to end up the same. Make sense? Ish? Sure. Okay, we can talk about it. Would you want? We can have office hours or something. We can go more in detail.
Thank you.
Like, yeah, sure, whatever. Okay. So what we're gonna be talking now is about. So far, when we're talking about forces and the effect that a force has, we always assume that when you have an object and you apply a force, that object is gonna move to one direction. It may stay still, or it may increase the velocity. We always assume that change is gonna be kind of in a linear motion. However, if you have an object and you apply two forces in opposite directions, then that force can rotate. Now, we haven't talked about rotation because when we talk about objects, basically what we do is that if we have any object what we do is that we assume that this object is going to be a point. And by definition, a point cannot rotate. It doesn't have any dimensions. It doesn't have any, it's completely symmetric, so there's no rotation of a point. So what I want to do now, what are things that we're going to do now is that we're going to try to look at those rotational motions. So what we're going to do is that instead of working with points, with the point model, we're going to change and work what is called an extended object model. Okay, an extended object, basically what it's going to try to do is that we're going to have an object and we're going to try to keep that geometry as much as we can. We're going to try to do a simplification, but by keeping some of the dimensions that are relevant to the object. So a bird is still a very complex geometry, it's a very complex structure, but I may be able to change the bird by a box, by a square. And as long as the dimensions of this box is similar to the dimensions of the bird, and as long as the mass of this box is equal to the mass of the bird, I can say that this box is a model of the bird, and I can apply some equations on it. Okay? And that's something that we're going to be doing in physics a lot. We ignore the shape and we create a model of it, even though the model seems to be very simplified. But by the things that we need to do with it, this is more than enough. So now instead of talking with a point, we're going to talking about, in this particular case, we talk about a box with dimensions. So now in this case, we can actually rotate this box and we can be talking about things that rotate. Okay. Now, the same way that we have force and the force creates a linear motion, there has to be something equivalent to the force that creates a rotational motion. Okay, and that something is what we call torque. And torque, I use this Greek letter, the tau, to talk about torque. So the same way that if something is moving is because the sum of forces are not in equilibrium, and that creates the object to move. When something rotates, is because the sum of torques or the net torque is different than zero, and that object is going to start rotating. Now, torque is particularly important for us because every single joint that we have in our body is going to be a pivot point in which an object is going to rotate. So if you think about your elbow, well, your elbow is a pivot point and your arm rotates along that pivot point. Your shoulder is going to be a pivot point for your arm. Same as your jaw, your neck, pretty much every single motion that we have in our body is some kind of rotation. So actually rotations tend to be a little more important for us than forces. Well, kind of. But that's what we're going to talk a lot about torque. Okay, torque. This couple of topics that we're going to cover. This is sections 7.3 and 7.4 of your textbook. So we're going to be talking about this, and then from here we're going to jump to chapter 8. Okay, but the ones that specific talk about torque is 7.3 and 7.4. Okay, so let's assume that we have an arm, and this is an arm. Okay. Okay, and I'm gonna assume that look at the torque at my elbow. Okay, so one of the first things that I'm gonna do is I'm gonna simplify my arm, and I'm gonna work with an extended model. So instead of having this arm, I'm gonna have something like this. Okay, and this is gonna be my my elbow. That's the little point. I'm gonna draw just the arm somewhere around here. I'm not gonna put it at an angle. Okay, so instead of drawing the whole shape of your arm, you just do it a rectangle, and that's gonna be good enough. Your elbow is the point in which your arm is gonna rotate. So we're gonna call this the pivot point. Okay. Now I'm gonna apply a force on your arm. You can imagine that someone is pushing you, someone is pulling on you, you're catching a ball, you're catching an object, and there's gonna be a force pulling down like this. Okay. Now, what I'm gonna do is I'm gonna draw an imaginary line, and it's gonna be a line that goes from the pivot point all the way to where my force is being applied. So I'm gonna have this imaginary line. Okay, and this line I'm gonna call it radial. It's called the radial line or the radial axis. Depends on the book. I think your book is radial line. And it's just that. It's a line that connects the pivot point to where you apply your force. Okay? Now, there are a couple of things that I can measure. I can measure the distance from the pivot point to the force. So this distance is going to be the radius, r. And the other thing that I can measure is this angle over here. And the angle, this one, is basically the angle between your radial axis and your force. There are two angles. You have this angle and you have this other angle. We're going to take the one that is less than 90 degrees. Okay, and the way, so yeah. So yeah, we're going to assume that phi can go phi, how do you pronounce it, phi? Goes between 0 to 90 degrees. Okay, and the way you're going to calculate the torque, or one way to calculate the torque, is basically by saying we're going to calculate the radius times the force times the sine of phi. And I'm going to explain later why we have this sine theta, sine phi. But that's going to be how you calculate torque. If we look at the units, we have the force in meters and we have the distance, sorry, the force in newtons and the distance in meters. So the torque is going to be in newtons meter. Now we we know that the force is going to be a vector. The radius is a scalar, so the torque has to be a vector. And normally, if you think of your elbow can rotate in every single direction. I mean, it can rotate in 3 dimensions. So the torque should also be in 3 dimensions. However, for our class, we're always going to be assuming that whatever is rotating is going to rotate in the same plane as your piece of paper. So your torque can only have 2 directions. Either it's clockwise or it's going to be counterclockwise. That's the only 2 directions that you can have. So clockwise anti-clockwise torque is going to be positive, and negative torque and clockwise motion is going to be negative. So in this case, this force, you can imagine that it's pushing you down, it's pushing your arm down, so it's moving your arm in a clockwise direction, so this will create a negative torque, yeah? Makes sense? So I'm gonna go and explain why are we using this sine of 5, and it's not always gonna be sine of 5, so you have to be careful with this angle. So I'm gonna redraw this just in a new piece of paper. So I have my arm. And I said I have my radial axis. And oops. And I'm gonna have my force here. And this angle is gonna be 5. Now, the same way that when we have a tilted plane, we tilt our frame of reference. We're gonna do the same when we are working with torque. We tilt our plane of reference so that one of the axes is gonna be along the radial line. Because this object, this arm, can basically rotate anywhere on 360-degree angle, we don't call it X and Y. We call those axes. The one that's parallel to the radial line, we call that the parallel axis. And the one that's perpendicular to the radial line, we call that the perpendicular axis. We call it, we just call it like that with those symbols over there. Okay, now this is one of the tricky parts with torque. There are this force, because it doesn't align with the perpendicular or with the parallel or the perpendicular axis. This force is going to have two components. It's going to have a parallel component and it's going to have a perpendicular component. Yeah. Now imagine that you have a force and you only have that parallel component. I would usually do a demonstration, so you can imagine that someone is pulling your arm away from you. So you have your arm straight and someone is pulling it away. Your arm doesn't rotate. If they pull really hard, they may even be able to dislocate your shoulder, but it's not gonna rotate your shoulder. So this force over here doesn't rotate at all. You can stretch it if you have a very soft material. If it's going into the opposite direction, you may compress the arm, or you can make it more stable, but it's not going to rotate it. The only part of the force that rotates is the perpendicular component. That's the only one that rotates. Or only the perpendicular component causes rotation. Okay, so to calculate the torque, we need the distance between the pivot point and the force, and we need the perpendicular component. Given this angle phi, then this perpendicular component is r times the force sine of phi. If I have give you a different angle, for example, that angle alpha, then the torque will be r. It still will be the same. I need a perpendicular component, but now the perpendicular component, I can calculate it as far rf cosine of alpha. So you have to be careful with what angle you have. What you need to be what you need to calculate is that perpendicular component of the force. Okay. There are different ways that you can try to calculate the torque. And I'm gonna do another drawing over here. So I have my arm. And I'm gonna say that my arm that is an angle phi from the horizontal, okay? And on one, on my hand, I'm holding a dumbbell. And that dumbbell, well, it's gonna have a weight. And that weight is the one that is actually pulling my arm down in this case. It's gonna rotate clockwise. Okay, so especially when you're working with human body, when you are looking at torques in different joints like your hip, your knees, sometimes measuring these angles alpha, these angles phi are not that simple. So another way is by using what's called moment of arm. Okay, so the way you calculate the moment of arm is that you have your arm, or you have the object that's going to rotate. You have the force that's being applied, the weight of the dumbbell in this case. And I'm going to draw a line that is just, it's an imaginary line that just go in the same direction as my force. Okay? And then what I'm going to do is I'm going to find the shortest distance between my pivot point and that imaginary line. And that's always going to make 90-degree angles with the force line. So the shortest distance is going to be this one. It's always going to make a 90-degree angle. And this distance, that's my moment R. And in this case, notice that I have a triangle rectangle. The hypotenuse is the distance R, it's my radius R. And the moment arm is will be R, oops, cosine of phi. And the way you calculate the torque is basically by MA times your force. And this will be the force cosine of phi. I'm not going to call this phi, I'm going to call it theta, just to not confuse it with the other one. Okay, makes sense? So those are two ways that you can try to calculate the angle. If you want to see it in terms of phi, so I'm gonna call this angle phi. And so this triangle rectangle, this is phi, this is R, and I want to calculate the length of this guy over here, then MA will be R sine of phi. So your torque will be R sine of phi times F. which is what we have before. Yeah. If it doesn't make sense right now, don't worry. We're going to be working with the moment of arm later. In general, if you can work with the moment of arm, is way faster than try to work with the perpendicular components. But sometimes you need to work with perpendicular components and you decompose your force and all that. Okay. Questions? Emma? Mary? Okay. So let's do a couple of problems if it start making more sense. So again, I'm gonna have my arm. I'm gonna ignore the mass of the arm. It's not something that we will do all the time, but right now I'm gonna ignore, and I'm gonna assume that my arm is, the weight is negligible. And here at the end of my arm, I'm gonna have a dumbbell, and this dumbbell has a mass of 20 kilograms. I'm gonna say that the distance between my elbow and my hand, I'm gonna say that this distance is 45 centimeters. Okay, so what I want you to try to do is to calculate what is the torque. Okay, so give it a try, see if you can try to calculate the torque on your own. So remember, for the torque, you need pivot point, you need a radial distance, you need an applied force, and you need an angle. So try to identify those in the figure and then substitute in the equation.
I don't know what to do. I don't know if there an angle.
Yes, there's an angle. So draw the force. Which direction is the force? What force do you have, first of all? What is the force that's causing your arm to rotate?
So, you said the limits was the newtons and amperes.
Okay.
So would I need to convert it to meters?
Yep. So the angle that you're looking for is the angle between the force and the radial one. Okay.
force be going outwards?
So the force in this case is the weight of the dumbbell.
Okay, so it'd be going down, okay.
Yeah, so the force that you have is the weight of the dumbbell, which would be the 20 kilograms at 9.8 newtons per meter second. Now, the angle that we're looking for is the angle between the radial line, which is going to go from your pivot point to wherever the force is applied. So you're looking for the angle between this line and your force. So it's going to be this angle, which in this case is 90-degree angle. Okay.
The momentum equation, is that mu times A or is that M times A?
It's MA, it's moment boundaries. Yeah, they're confused that with the coefficients.
I know.
So you're gonna apply. So you have the range is the most. Okay, so this force is going to be 20 times 9.8, which is how much? 198? 196 newtons. Okay, this angle is going to be 90-degree angle. So the torque, the way we calculate torque is R times the force times sine of phi. R is the distance between the pivot point and the force. It's 45 centimeters. I'm going to convert it to meters. So this is going to be 0.45 meters times 196 newtons sine of 90 degrees. Sine of 90, this is going to be 1. And this is going to be, what you got, Emma? 88? 88.2 newtons per meter. Okay, this is the magnitude. Remember, we are working with a torque, and a torque is a vector. So we need to find out what is the direction of the vector. So you can imagine that this dumbbell is moving your arm clockwise. So this torque is going to be a negative torque. Okay. Make sense? Ish? Okay, this one is going to be just a piece of wood. The length is 1 meter. And the pivot point is going to be 25 centimeters from the left edge. then we're gonna have two forces. One force has 20 newtons. It has an angle of 40 degrees. And then this one is going to have a magnitude of 30 newtons. Okay. Now, what I want to find out is what is the net torque. And the net torque is basically the sum of all the torques on that object. So see, this will be T1 plus T2. So I'm going to call this F1, and this is going to be F2. So the net torque is the torque created by force number 1 and the force created by force number 2. Okay. So give it a try.
Down. Down. Just like a, it doesn't have to be the towel itself, it's just like a very fancy tea.
Very fancy too.
Very fancy tea. Don't use the tea because then we're gonna be using time and period and stuff like that, so it gets confusing. So the towel is like
It's like a tie with a fancy hat. I don't know how to explain it. Yeah, usually I guess like has a little curve and it's kind of very fancy and it's just I just do a T with a funny stuff. Yes.
So here, are we using lid or just?
Just that part. So you only look at the distance between the pivot point and whatever the force is. So it will be so the radius is always going to be the distance from your pivot point to wherever your force is. So remember to work with meters.
Okay,
And remember also that they have sign, so it can be positive or negative. So when you add them,
so would, these ones be positive?
well, so the way you do it is that you ignore one force.
Yeah,
You look at this one. So this one is rotating you clockwise. So this one's going to be negative.
okay,
And then this one, the perpendicular component, is pushing you counterclockwise. So that's going to be positive.
okay.
Yeah, just be careful with the signs. So one is going to rotate you clockwise, and the other one's going to rotate you counterclockwise. You want to? You want to? No? Yeah,
so real. Let me see.
Okay, so I'm gonna calculate first the torque from the first force. And again, this is gonna be the radius times the perpendicular force, and this will be 0.75 meters. The force is gonna be 20 newtons, and the angle between the radial axis and my force is 40 degrees, so this is gonna be sine of 40. Okay, that's gonna give me this perpendicular component. That's the one that I need to calculate the torque. So if anyone can give me the, what value you got?
I got 9.64.
9.64 newtons meter. Now, this force is rotating counterclockwise, so that's gonna be positive. Okay. For tau 2, I'm gonna look at the F2, so that will be 0.25 meters times 30 newtons. And again, the angle that I have is 90-degree angle. It's a 90 degrees. So this will be sine of 90, which is just 1. So this will be what? 2. What do you guys got?
7.5.
7.5?
Yes.
7.5. Now, if you just look at that force is going to rotate you clockwise, so this is going to be negative.
How do you know what direction the force is rotating?
So you look at your pivot point, and let's say that I'm looking at F2. So I'm going to ignore F1 completely. So if I only have F2, and this thing is pushing me up, the whole object is going to rotate counterclockwise. Yeah? If I want to know this force, I look at the perpendicular component and it's pointing up. So this thing, if I were to push that way, this is going to rotate like that. Yeah, that's the easiest way. So this is going to be negative. So tau 1 plus tau 2, I will get 2.14 newtons meter. So that means that at the end, this thing is rotating counterclockwise. Make sense? Harry? Yeah? 13? Did I pronounce that correctly? Ish?
Yes.
Okay, I'll keep trying. Alex? Kayla? Brianna? Shall we go? Yes? It's like 7 minutes. I'm hungry. I'm tired. Okay, let's go. Wait. Does anyone have any question?
I have a question on homework that I want to ask.
Okay, you can ask me at the end. Yes.
Can we leave the homework here?
If you're done with the homework, yes, you can give me the homework.
So you gave us like a bunch of equations. Is the T equals R, force sine, whatever, the one that we're always going to be using?
Not always. We're gonna do a couple more examples. Don't give you a bunch of equations. I give you the tools that you need to solve the problems. It's like there's like a bunch of equations.
There's a bunch of equations on my
We'll do it slowly, and I will help you develop the tools necessary to solve life problems with physics and science. Okay, guys, see you